Let's take a general case of the circular ring and the circular disc, which is the annular disc, for which we will find the moment of inertia about the axis passing through the center and perpendicular to the plane of the disc, for which we will consider that disc is composed of the elementary rings. We'll find the moment of inertia of the elementary ring, and then we'll integrate to find the total moment of inertia of the annular disc about the axis through the center and perpendicular to the plane of the disc. So first we will draw the diagram for the annular disc. Suppose this is the outer ring and it has inner ring, and the mass is distributed inside the area of the between these two rings. The distance or the radius of the inner ring is say A and outer is B. Because mass is distributed uniformly over the area, therefore we will take some elementary ring of radius, suppose R. So this is the elementary ring of radius say R, and its thickness is suppose dr. Therefore we can mark it is R, and the thickness of this elementary ring is dr. So first we take that area mass density, that is represented by sigma, equal to total mass by total area. The mass is suppose capital M, and area is the area between these two rings of radius A and B, and it is outer ring has the area pi b square minus inner has pi a square, and it is equal to M by pi into b square minus a square. And the area of elementary ring is equal to circumference, this is 2 pi r, into thickness, this is dr. So mass of elementary ring, which is represented by dm, it will be equal to the mass density sigma and the elementary area dA. This is equal to m by pi b square minus a square, and area is 2 pi r dr. First we will consider the ring for which moment of inertia is elementary, because mass is elementary and it is written as that dm into r square, because distance of the ring from the center is r, and substituting the value of dm, it is m by pi b square minus a square into 2 pi r dr into r square. So total moment of inertia will be equal to integral di. Substituting the value of di, it is m by pi b square minus a square into 2 pi r dr into r square, and variable term is r, so we have to substitute its limiting values. The value is r equal to 0 at center, and at outer it is r equal to b, and for inner circle r equal to a. Because mass is distributed from a to b, so limits will be r equal to a to b, and it will be equal to, taking the constant terms out of the integral, it is mass m pi b square minus a square, then 2 pi, and remaining term will be r equal to a to b and r cube dr. Here pi get cancelled, so it will be equal to 2m by b square minus a square, and integral of r cube is r raised to the power 4 by 4, and limits are r equal to a to b. 4 is constant, so it is taken out, and we will have 2m by 4 b square minus a square, and then put upper limit first, it is b4 minus, and then lower limit, it is a4. This 2 is get cancelled, so we will have 2, this is m by 2 b square minus a square into b raised to the power 4 minus a raised to the power 4. On factorizing, we will have m by 2 b square minus a square into b square minus a square. This is the factor of b raised to the power 4 minus a raised to the power 4 into b raised to the power 4 b square plus a square. This b square minus a square get cancelled, so finally we will have half m b square plus a square. For annular disk, the moment of inertia will be I equal to half m b square minus b square plus a square if mass is distributed uniformly over its area. Now, for a special case, suppose a equal to 0. If a equal to 0, then this is the case of circular disk, and the moment of inertia about the axis perpendicular to the plane and through center, this I will be equal to half m b square, which we have already discussed. And if a equal to b, then this is the case of circular ring, and in that case I will be equal to half m b square plus b square, that is equal to half m into 2b square, and that is equal to mb square, which is also discussed earlier in case of circular ring. Let's take some examples.